But today's problem is going to be valid Sudoku. So essentially, you're going to be given a 9x9 Sudoku board. It's going to be called board. And we have to check whether this 9x9 is valid or not. Well, this is literally just the Sudoku rules. So each row must contain the digits 1 to 9 without duplicates. Each column must contain the digits 1 to 9 without duplicates. So the rows, and then next to the columns, and then each 9 3x3 sub-boxes of the grid must contain the digits 1 to 9 without duplicates. Return true if the board is valid, otherwise return false. Note, a board does not need to be full or solvable for it to be valid. So basically, what they want us to do is to make sure that every row and every column and every 3x3 does not have duplicate values, right? So I guess if you look at this row, if I have 1, 2, like this, and if I have a 2 here, then when I check this row, we'll find a duplicate, right? There are 2 2s here, so that's not valid. Same thing here, if I have a 2 here, then this column is not valid. Or if I have a 1 here, then the row is valid, the column is valid, but the 3x3 here is not valid. So this is just a check for duplicates problem in disguise. So how do we go about solving this thing? Let's take a look. So there are 2 methods to solve this. The first one is brute force, but unlike other problems, brute force is actually not bad. It's genuinely not bad. So brute force is literally like, okay, I'm gonna check every row, like that, and all the way here to check for duplicates in the rows. And once I've checked all the rows, I'm going to check all the columns, 4, 5, 6, 7, 8, 9. So I'm going to check all this, then check all this, all this, all this, and so on and so forth. And then after that, we're going to check 3x3. So I'm going to check this box, and then I'm going to check this box, so on and so forth. So if you think about it, we're basically reading the entire board 3 times, right? So 1 time through the rows, another time through the columns, another time through the 3x3s. So the time complexity here is actually going to be O of, well, I'm going to say n is going to be the length of the row. So it's going to be O of n squared to read the board once. Since we're reading it 3 times, it's 3n squared. And as for the space complexity, we basically only need to remember 9 elements at any given time. So it's basically O of n. And the second solution here is the quote-unquote smarter method, which is to use a hash map. Now, the thing with this one is that the time complexity, instead of reading the board 3 times, we only read the board 1 time, so it's going to be O of n. But to achieve that O of n, it's not through a smart algorithm or anything like that. It's literally just using a hash map to remember things. So the space complexity is going to be O of, well, you'll see. Let's calculate it together. So by reading the board once, we just have to remember everything, right? So let's say I'm going to read an element at a time going like this. So I'm going to read the row, and then I'm going to read the next row, and the next row, and the next row, and so on and so forth. So as I'm reading the row here, so when I encounter an element, I have to remember it. So I'll have 3 hash maps. I'm going to have a row hash map, a column hash map, and a 3x3 hash map. And for the row, it's probably going to be the smallest size because I'm reading things row by row. So after I read this row and I conclude that there are no duplicates, I can forget about this row entirely and move on to the next row. And then once I'm done with that row, I forget about this, move on to the next row. So I can clear the hash map here after every successful row reading, right? Basically, I only have to remember n objects at a time. And as for the column, this is actually going to be our largest one. So if you imagine I'm reading row by row, if you think about this from the columns perspective, it's like, okay, I have like 9 columns started, but these 9 columns only have 1 element each. And then I read the next row. Now I still have my 9 columns, but they each have 2 elements. And so on and so forth. So basically, we won't be able to clear the columns array. It's not going to be until we read the final row. We basically have to store the entire board in memory to keep track of the columns, right? So the size of column is going to be n square objects. And then for the 3s, these are a little bit trickier, but it's also not too bad. So if you're reading it row by row, so at this point, you can imagine we have 3 of these 3x3s, and then we've only read the first row of each of them. And then once we start processing the second row, we can't really clear this out yet. But once we've read the third row here, then we can finally conclude whether any of these 3x3s are valid 3x3s or not, as in they have no duplicates. And if all of them pass, and it's like, okay, this one seems valid, there's 1, 2, 4, 9, 8, and there's no duplicates in this 3, no duplicates in this 3x3, no duplicates in this 3x3, then I can clear this. And I can move on to processing the next set of 3x3s. And then I can clear that, and then I move on to the last set of 3x3s. So how many elements is this? It's like 3 times the row size, right? So 3n. So I'm going to say it's like this. So the space complexity is going to be n for the rows plus n squared for the columns plus 3n for the 3x3s. Now, if you kind of condense everything down, this should be n square, right? Because we're getting rid of the 3. And this should be just n square for the space complexity. Oh, sorry, the time complexity for the hash map should be n square, because we're reading through the entire board, right? So every row and every column. So looking at this strictly from the condensed view, it looks pretty bad, right? Like somehow brute force is better than the hash map solution because this is n square and this is n. Well, this is still n square and this is n square now. I will admit it does look worse, but if you look at the constraints of this problem, this one here, we can see that the board length is actually 9. So it's always 9 units long and the column is always 9 units long. So because the n is like relatively small, you can feel like the scaling factor of 3 more. Like proportionally, the 3 is gonna matter more in a smaller n, right? Because usually we kind of ignore the scaling factor if like the n is so large that this linear multiplication just doesn't matter anymore. Before we move on to actually writing the pseudocode or high-level code overview for this, I want to show you the input. So the input looks something like this. So this board on the right is basically going to be represented as a 2-dimensional array where every row is going to be like this, right? And then all the empty spaces are going to be marked with this dot. And then the output is just a Boolean, true or false. Okay, in all honesty, like this question doesn't have like a clever algorithm or like a trick or anything like that. I think this is just straight up testing how comfortable you are navigating like a 2D array. And also I think the most unintuitive part is going to be checking the 3s, right? Because of course everyone is used to writing the double for loops to check for the rows and columns, but 3s is not a problem we have to deal with often. So that's going to be a little bit trickier. So with that preamble out of the way, let's just get started. So actually I'm just going to go straight into coding because there's not much to explain. We just got to code. So let's start off by defining a couple of variables here. We've got row size, which is the length of the board, and the column size. Basically, if you imagine this as like a bunch of arrays, right? If each row is an array and board is actually an array of arrays, if I take the length of board, that's counting how many subarrays we have, right? Which is also incidentally counting how many rows we have, which is why row size is equal to the length of board. And if I do length of board 0, so what is board of 0? Board of 0 is like one of this. We take the first row, right? And then we take the length of that, which is like this thing, right? Dot, which is the columns, which is why this is going to be call size. And then once that's done, we got to start checking every single row, every single column, and every single 3x3, because we're going to be starting with the brute force method. We're going to start with for an I in the row size. We're going to loop through every row, and then we're going to need a set. I'm going to call it a scene, which is going to keep track of all the elements that we've seen so far. And then I'm going to do a for j in the column size. So this is probably the easiest one to comprehend, but we'll just go through it anyways. We're effectively going to be moving row by row, right? So the I is going to be this row, and then we're going to go through each element in the row. And then once that's done, we're going to move on to the next row, and then we go through the columns one by one. Very straightforward. And then what are we going to do for each element? Well, first things first, we got to do a check. So if that element at ij isn't seen, it means we found a duplicate number while going through the board row by row. So because we found a dupe, then we can return false. It's not a valid Sudoku. But if it's not in scene, that means we have to add that number into our set, right? So we can just say scene.add that element. But before we conclude this section, we do have to add a little if check here. And that's going to look like this. We're going to be adding that element into the scene set if that element is not dot. Why dot? Because remember, in our input, the dots indicate an empty space. So if it's a number, we want to check whether we've seen this number before. If we haven't seen it, we add it in. Same thing with this. But if we've encountered a dot, we just skip over it. We're not going to add the dot into our scene. And that's going to be the first part, where we check the rows. Let's go to the next part. And then now we have to check every column, because we're going to be going through the entire board 3 times. The first time is row by row, the second time is column by column, and the third time will be every 3x3. So let's move on to checking the columns. The code is really similar. It's just that for the outer loop, we're doing j. We still have the same scene set, and then our inner loop is going to be I. And then the rest of it is literally the same. So what does this actually look like? Let's have a look at the visualization, right? So we start with the for j, and we know j is going to start here at 0, and then we're going to go for I. The for I loop is going to go down here, all these rows one at a time, right? So once we've worked through all the rows, then we increment j to move on to the second column, and then we're going to increment I one by one through each row. Whereas in the previous section where we did a for I and for j, where we started with a row and then we went through each column, this time we're starting with a column and then going down each row. So that's also pretty straightforward to understand. And then once we've checked the columns for duplicates, it's time for us to check the 3x3s. This is probably the most tricky section. So let's think about how we want to do this, right? We actually want to start with our I. We probably want something like this. For I in range 0 to 3, right? So I is going to go here, and then go here, and then go here. Okay, so but what do you want to do for each row here, quote unquote? I want to do a for j in range 0 to 3, right? So that's going to look like this. It's going to start with I is 0 here, and then we're going to say j is 0 here. So we're going to process this element, right? And then after that, we're going to increment j here and process this element to this. And once that's done, we're going to increment I here, do these 3, I here, do these 3. Now the question is, how do we go into this tile, and then this tile, and then this tile? Well, we can't just keep writing for I in range 0 to 3, and then we got to do a for j in range 2 to 6, right? 3, 4, 5, and then 6 would be the barrier here, right? It's going to be really troublesome for us. And we got to do the 0, 3 again for I, and then the j would be like 6 to 9, right? And then once we've done these 3, then we would finish these 3 basically, right? And then we got to move on to the next section where this time the I will be in range 3 to 6, right? Because this is number 3, 4, 5. And then we do the same 3 j's again. It's pretty cumbersome. Let's do a better way. So why don't we write a for loop that goes something like this? For row start range 0 to 6, and then we're going to jump 3 steps. So I'm basically marking the rows that I'm going to be starting it at. So row start, as the name suggests, is going to start at 0. And then the next iteration, it's going to start at here. And the next iteration, it's going to start at here. And then we're going to couple that with the for call start in the same thing. Range 0, 6, 3. So in conjunction, it's going to look like this. For the first row start, the value is going to be 0, right? It's going to be 0 at first. So we're starting here. And then call start is going to start here. So these two values indicate the start of this tile. So in the next iteration, once I move call start to 0 plus 3, which is index 3 over here, this indicates the start of this block. And then once again, once I'm in the third iteration, when the call start is 6, it's going to indicate this tile, basically, right? Then row start is going to move here, call start is going to reset here, and then it'll indicate this tile, and so on and so forth. So, okay, cool. We have this thing to indicate the start of it, but we haven't actually processed any of the elements. Now, this is where we need another for loop, can you believe it? For I in range, row start, and row start plus 3. And we need another for loop for j in range, call start plus 3. It's quite horrendous having 4 nested for loops, but it's pretty necessary. So initially, row start is going to be here and column start is going to be here. And then the I is going to start here and j is going to start here. Is we're going to process this tile and then j is going to move. We process this tile and we're going to move and then we're going to process this tile, right? Because it goes all the way to call start plus 3. This will be the barrier. Once we're done with j, we're going to reset j and increment I to here. And then we do the same thing. Process this element, process this element, and process this element. And then we repeat that for the final row as well. This. And once we're done with this, we're actually gonna move the column start to 3 steps up. So it'll be here. And then I is gonna start at row start to row start plus 3 here. And then j is gonna start here and we'll go up to column start plus 3. So here. So it's gonna process this thing and so on and so forth. And of course, it kind of goes without saying that once we've processed this tile, we're gonna move CS here and then we'll process this tile. And then once that's done, we'll finally move RS down here and CS will restart from here. I is going to restart from here and J is going to restart from here. And then we do the same song and dance again until we've done the whole board. Now that we understand that, we can move on to the actual code. For a 3x3, it's just as I said, we need these. But before we start defining the I and J, we need to set a scene set. But before we move on to the I and J processing, we have to define a scene set as usual. And then we'll have the I and J's look like this. Let me make this smaller so you can see. Function's getting a little bit long. And then the rest of the checks are exactly the same. If that element's been seen, then this is not a valid Sudoku board because we found a duplicate in the 3x3s. But if you've not seen it before and it's not an empty slot, then we add that into the scene set. And that's pretty much it. And if it passes all the duplication checks, we just return true. There you go. That's the brute force solution. Okay, next let's try the hashmap solution. So in the hashmap solution, we're going to be looping through each element row by row and then column by column, and we're only going to process each element once. Unlike brute force where we processed everything 3 times in total. Every time we process a new tile, if it's a number, then we have to cache it inside our set. So I'm going to create 3 sets. Well, it won't be a set this time. It'll actually be a dictionary. So I'm going to start with defining this. Row default dict set. Basically, the plan is once we're done processing the board, our row dictionary is going to look something like this. The key is going to be the index here. So the index of the row, because we have indexes 0 all the way up to 8. So for the first row, we'll have a set of 1, 2, 3. And then our next element will be 1, which will have a set of 4 and 5, right? You can see that in the drawing to the left. And then the next row will have the set of 9, 8, and so on and so forth. That's going to be the format. And then we'll do the same thing with column. It's going to be a default. With the column at 0, we're going to have 1, 4, 5, 7. And then the next one, we're going to have 2 and 9, and so on. And for the 3x3, this is where it's going to get a little bit funkier. Because I can't easily identify the 3x3s with like a single number, I'll need a tuple to help me store the key. So remember in the brute force solution, we use the starting position of the rows and columns to determine the 3x3s. So it will be the same thing here. So for the first one, I'll need a 3x3 that starts at 0, 0, which is going to be the set of 1, 2, 4, 9, 8. And then next, I'll need the 3x3 that starts at 0, 3, which is going to give me 3, 5. And then just as a random example, I'm going to jump to the 3x3 at 3, 3, which is going to be the middle 3x3, and that should give us 6, 8, 3, 2. So this is the format of the dictionary that we want. We need proper identification for each row or column or 3x3, and in the 3x3, it's most natural for us to use the tuple. So let's get to it. The first check is going to be the most straightforward. If it is an empty space, we just ignore it. And for our next check, we're going to check whether that element is inside row I, right? Because we have the row number here, so we know which row this element belongs to, right? So if this element is inside that row, then we're going to return false. The next check is also very straightforward. It's basically a carbon copy. If it is inside hole J, then we return false. Now here is where it gets a little bit tricky. As for the third check here, I'm doing this. Honestly, if you break this down, it's not that bad. Because we know that the goal of this expression is to somehow round down our I and j to these tuples. So let's see it in action. Back on the blackboard here. So let's take this element, for example, this 1. So we know that it's on I is equal to 7 here, and then j is equal to 4 here, right? That'll be board 7, 4. So we'll start with this expression, 7 floor divided by 3 times 3. So what's this going to give us? This is going to give us 2.333 whatever, right? With a normal division, but with a floor division, then it's going to get rounded down to the smallest integer. So this is going to be gone. We're going to be left with 2. And then it'll be 2 times 3, which will give us 6. And 6 is over here, right? I equals 6 is over here. Which is correct. This is pointing to the correct row here. Let's have a look at the column then. It's literally the same expression. When we plug it in, we're gonna get 4 floor divided by 3 times 3, which will give us 1.33 whatever, which will get rounded down to 1 times 3, which will give us 3, which is over here, right? So you can see the similarities to our brute force solution. Now we have a tuple that points to the start of the 3x3. Excellent. So with this expression, we can successfully condense every pair of I and j to their corresponding 3x3. And then of course the expression in the code is a little bit longer, wasn't it? So it had these 2 brackets outside. We're just gonna turn this into a tuple. And then it has a 3's here, closing it, right? So effectively, we are saying this. So we're saying in this 3x3, does the number 1 already exist in this 3x3? And then the rest of the logic is exactly the same. If the number 1 already exists in this 3x3, then this is not a valid Sudoku. But if it doesn't exist in the 3x3, then we add this into the dictionary. Okay, so we'll have 631 or something, right? Because we're going to be chucking that 1 in here. Anyways, let's go back to the code. Here's that expression that we just broke down. So if that number is in that 3x3, then it's a duplicate, which means it's not a valid Sudoku. And then the rest of the code logic is pretty simple. Once we're done doing these checks, we're just going to add that number to the row, add that number to the corresponding column, and finally, add that number to the corresponding 3x3. And that's it. We return true. If it passed all of these checks, give it a run. there you go. Looks pretty good. So if you notice in our row dictionary, we're actually storing 9 different rows, aka every single row in the board, and then column we're storing every single column, and the threes we're storing every single 3x3 inside the board. So the space complexity for this code specifically is gonna be O of 3 times what? How big is one of this? And square, right? Which is quite different from our calculation earlier, which was something like this, right? Well, that's because we didn't bother clearing the rows. Technically, if you want to optimize for space, you'd have to clear a row every time we finish one of these J for loops. And then for threes, the key is not going to be a tuple anymore. It's just going to be the column. And we'd have to clear threes every 3 cycles of J. But I think the solution is good enough. As you can see in our stats here. So I'll leave the code as is for now, but I guess if you're really interested in optimizing space, this is something you can try for yourself. Alright, that's all. Okay, bye.